So we're still in the 2010 Waves paper. Question 3 on refraction. Jane puts a glass block on top of a coin in a trough. She then pours water over this. The diagram below shows the situation. Now, straight away, I don't know why anyone would do this, except for a physics experiment, but I guess it models some really important concepts which then apply to other things. So let's continue. The arrow represents a ray of light travelling from the coin through the glass. The refractive index of glass is 1.55, which is higher than the refractive index of water, 1.33, which is again is higher than the refractive index of air. So we've got a decreasing refractive index the further out that we go. Complete the diagram to show what happens to the ray of light as it enters the water and then travels into the air. So what they're expecting here is for you to work out which way the light ray will bend. The assumption is that the light ray will pass from the glass to the water and then again from the water to the air. If it hits at an angle greater than the critical angle, there'll be total internal reflection. But we're going to assume there's no total internal reflection, so assume no total internal reflection, and then we're going to draw on this diagram. In fact, I'm going to scale it up a little bit just for the sake of clarity. We've got a light ray coming from the glass down here. It hits somewhere there. Here's our normal, and it's going to bend either towards the normal or away from the normal. We're going from glass into water. Remember, glass, water, air. Glass being more dense with a higher refractive index, so that's travelling into a less dense, optically dense, so it's going to bend away from the normal, which means we'll have something sort of like this, and it will continue straight into the next boundary. And same thing again, because air is less dense than water, it's going to bend away from the normal once again, so we're going to have further refraction occurring. So as you can see, if I drew this on the little diagram here, it's a little bit hard to show those details. I guess you can show it, but it doesn't look too clear. Anyway, that's A. B. Use calculations to determine whether the ray of light will enter the air when the angle of incidence of the ray of light in the glass-water interface is 48.7 degrees. Okay, so that could be a little bit confusing. Let's just sketch on our diagram what we're dealing with here. So we have this, we're working out, well, we've got this angle here. This is our 48.7 degrees. We need to find this angle, I'll call it phi, and then, oops, no, we don't need to know that angle, we need to know this angle. Okay, and that angle is going to be the same as this angle, which will then allow us to work out this angle. So that's also phi, and then I don't know another, let's just scrap theta and reuse that, because 48.7, if that's theta, we're aiming for theta. So if theta is a real angle that we can actually find a value for, then we can tell whether the ray of light will enter the air. If theta produces some crazy kind of result on our calculation, then we can assume, or we can say that it's not. There's another way we could do this. We could try and find the critical angle for the air-water boundary, and if we then calculate what this angle phi is going to be, if phi is greater than that critical angle for the air-water boundary, then we know that there's not going to be any light rays passing through. But let's just proceed. What are we going to use? We're going to use Snell's law. N1 sine theta 1 equals N2 sine theta 2. And remember, these can look confusing, but it's really just two variables on each side rearranging. So we're going from the glass 1.33 into 1.55 sine of 48.7 and that should equal N2, which is 1.33 sine of the angle we're trying to work out, theta 2, which was phi in my above diagram, that one. So anyway, theta 2 is going to equal, and we rearrange this, so 1.55 sine 48.7 divided by 1.33, and then you have to take the inverse sine of what that number calculates to be. So I'm skipping ahead a little bit. You can spend a bit of time thinking about that if you're not comfortable with the equation manipulations. Yeah. So what do you get? You get an angle theta 2 of 61 degrees. That means the angle of incidence for the next boundary, which I'm going to do in a different colour. Okay, so here we go, different colour. Now N1 sine theta 1 equals N2 sine theta 2. This time N1 is 1.33 because we're going from the water into the air, and the sine theta is now 61 degrees, and N2 is 1.00 for the air, and then sine theta 2. And if you perform this calculation, you'll find theta 2 doesn't work. So you can try and do the calculation, and it's just not possible, it doesn't work. And that tells you that this is theta 1 must be greater than the critical angle, so you don't get any refracted rays. And in the second part here, explaining our answer, we're having total internal reflection occurring instead. Total internal reflection. So that means all of the rays, instead of passing through and bending away from the normal, they're totally internally reflecting from that water-air boundary. So if you were under the water, you would see that coin, if you're in the path of light rays, reflecting off the surface of the water, which is kind of cool to think about. As I said, the other way you could do this is by calculating the critical angle from air-water boundary. I'll just very quickly show you that, but we're going to come across to the side because we've actually finished with that, and I'll throw that in red. So N1 sine theta 1 equals N2 sine theta 2, and because we're dealing with the water-air boundary, N1 is going to be our water, so 1.33 sine theta 1 in this case is our critical angle, because we're trying to find the critical angle, and N2 is the air, 1.00, and sine theta 2 is going to be 90 degrees, because that's the greatest you can get angle you can get before it starts totally internally reflecting. That's when your refracted ray bends away from the normal so much that it travels along the surface. And anything beyond that, and you can't refract just a little bit, it'll get total internal reflection if you increase that critical angle enough. Yeah, you could kind of say that the critical angle is the angle, let's say it's the angle beyond which total internal reflection occurs. It's a bit hard to distinguish exactly where it is, so sometimes you might see it in a diagram saying that the critical angle is that point where total internal reflection occurs. But anyway, so you rearrange this. Sine 90 degrees is 1 times 1 is 1, so you've got 1.00 on the right hand side, divided by 1.33 equals sine the critical angle, and then you'll do the critical angle as the inverse sine of 1.00 over 1.33, because that is a reverse function. If you did sine -1 of sine theta, that would just be the same as theta. Okay, so that's just a little aside there. So those two functions will cancel each other out. And then I'm not going to calculate this, but whatever you get is definitely going to be less than 61 degrees. Because we could see from the earlier calculation over here that theta 1 is greater than the critical angle. And that's that.